All right, in this video, we're going to talk about chapter 3. We'll start chapter 3 dealing with numeration systems and whole number operations. What we'll look at is numeration systems, and then we're going to be looking at strategies for addition, subtraction, multiplication, and division of whole numbers. Now, this first section, section 3.1, deals with numeration systems. And in this section, we're going to recognize numbers, their origin, and their representation in numerals and models, recognize different numeration systems, including the Hindu Arabic system, and recognize place value and count in base 10. All right, now let's start with some definitions here. Well, a definition of what numerals are. They're written symbols to represent cardinal numbers. The face value of a digit is its numerical value. Different cultures develop different numerals for representing numbers. And these are a few of the numeration systems here that's given in this table. Now, because of time, we're not going to cover every single one of these. The ones that I want to focus on would be, of course, the Roman numeration system. And also I'd like to cover just the Hindu Arabic system for numbers. Those are the only two that I will cover in this video. Okay. Now, what is a numeration system, by the way? It is a collection of properties and symbols agreed upon to represent numbers systematically. So what you just saw here in this table are considered to be numeration systems, okay? Like Babylonian, Egyptian, Mayan, Greek, Roman, Hindu, Arabic, and then Hindu Arabic. Okay. Now, one of the ancient numeration systems is a Telenumeration system. With this system, they use single strokes or tally marks to represent each object that is counted. So in this case here, this will be part of the Telenumeration system where they use tally marks, and then when they get to 5, they use a slanted line to represent 5. And for each 5, you have 4, and then those 4 are crossed with a diagonal line. So this Telenumeration represents the number 13. This is 5, 10, 11, 12, 13. Okay. All right. Also, there's the Egyptian numeration system. Here they use we use tally marks for the first 9 numerals, and then Egyptians improved that tally system by developing a grouping system based on powers of 10. So here's a table that consists of the Egyptian numeration system, okay? So like the vertical staff represents the 1, and then you have the heel bone that represents the number 10. The scroll represents 100. The lotus flower represents 1,000. The pointing finger represents 10,000. The polywog or the burbot represents 100,000, and the astonished man represents 1,000,000. Okay, so an example of a number written in using the Egyptian numeration system would be something like this. If I wanted to use the Egyptian numeration system to represent 2,345,123, this would be the representation of that. For 2,000,000, we have 2 astonished men. That represents 1,000,000 each. And then for 300,000, we use 3 polywogs. And then for 40,000 would be 4 pointing fingers. And then for 5,000, we do 5 lotus flowers. And then 100 would be 1 scroll. 20 would be 2 heel bones. And for 3 vertical staff. Okay, that is the representation of 2,345,123 using the Egyptian numeration system. All right, now the numeration system that we're going to focus more on is the Roman numeration system. And this was used in Europe in its early form from the 3rd century. It is still seen today on cornerstones, on the openings of page books, and on the faces of some non-digital clocks. Okay. Some watches and some non-digital clocks do use the Roman numerals. And also, if you look at books, and it could be textbooks or whatever, usually they use Roman numerals in the opening part of books before they start using what they call the Hindu-Arabic system to number their pages. Okay, so this is what the Roman numerals look like. The I represents the number 1 using the Hindu-Arabic equivalent. The V is the Roman numeral for 5. X is the Roman numeral for 10. The L represents 50. C is 100. D represents 500, and M represents 1,000. Okay. So here, Roman numerals can be written using the additive property. Like, for example, if I have this, MDCLXVI represents this. The M is 1,000, D is 500, C is 100, L is 50, X is 10, V is 5, and I is 1. So if you add 1,000, 500, 100, 50, 10, 5, and 1 together, you'll end up with 1,666. Also, if I have C, 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 X, X, V, I, that's going to represent 328 because each C represents 100. So 3 of them would be 300. 2 X's, each represents 10, that would be 20. And then V is going to be 5 plus 3 of the I's, each representing 1. So 5 plus 3 will be 8. So that Roman numeral will be 328 in the Hindu-Arabic system. Now, to avoid repeating a symbol more than 3 times, as in I, a subtractive property was introduced. Like, for example, if I is used, if I is to the immediate left of, let's say, V, it is subtracted from V. That would mean that IV will be the Roman numeral for 4, because I is going to be 1 and the V is going to be 5. So 5 minus 1 will be 4. Okay. So the Roman numeration system does use what they call the subtractive property. And on the next page, you'll see the Roman numeral using the subtractive property. And in this case, like IV would be the Roman numeral for 4. That's 5 minus 1, which would be 4. IX, that's 1 from 10, which will give you 9. Now XL, X is 10, L is 50. So 10 from 50 will be 40. XC, that's 10, C is 100. 10 from 100 would be 90. And then CD, C is 100, D is 500. So 100 from 500 will give you 400. And finally, CM, C is 100, M is 1,000. So 1,000 minus 100 will be 900. Okay. Now, there's also a multiplicative property for Roman numerals. In the Middle Ages, a bar was placed over a Roman numeral to multiply by 1,000. The use of bars is based on a multiplicative property. So, for example, if I have a V with a bar on top, the V is the Roman numeral for 5, but the bar tells me to multiply that 5 by 1,000. So 5 times 1,000 would be 5,000. And also CDX with a bar on top. Well, let's do this. CD, that's using a subtractive property, that's 400. And then X is a Roman numeral for 10, so 400 plus 10 would be 410. The vertical bar on top tells me to take 410, multiply it by 1,000 to get 410,000. And for more greater numbers, we use more bars, like for this one. The V has 2 bars on top. So that means the V is a Roman numeral for 5. The first bar above it is going to be 5 times 1,000. The second bar on top of it means I need to multiply by 1,000 again. So 5 times 1,000 would be 5,000 times another 1,000 would be 5 million. Okay. Now, let's look at some homework problems that are similar to the ones in my math lab. If a cornerstone represents when a building was built and it reads MD CCCLXVII, when was the building built? Okay. All right, so now let's try to identify the year that the building was built. So in this case here, that M right here represents the Roman numeral for 1,000. And then plus the D is the Roman numeral for 500. Each C represents 100. So I have 3 of those. So 3 times 100 would be 300 plus L, that's 50. The X is a Roman numeral for 10. The V represents a Roman numeral for 5. Each I is a Roman numeral for 1. There are 2 of them, so that'd be 2. So let's see, if I add 100 plus 500 plus 300, that's 1,800. Plus 50 plus 10, that's 1,860. 5 plus 2 is 7. So that means in the year 1867, that is when the building was built, in 1867. Okay. All right, and here's another example. At the end of the movie, the year of the copyright date is given in Roman numerals. If the number reads MCMLXXV, when was the movie made? So we get MCMLXXV. The M, of course, is a Roman numeral for 1,000. Now notice we got CM. C is 100, M is 1,000. Here we use the subtractive property. 100 from 1,000, that's going to be 900. And then plus the L, that's 50. Each X is a Roman numeral for 10, so 10 plus 10, that's 20. And the V is the Roman numeral for 5. So add 1,000 to 900 to 50 and 20 and 5, we'll get 1975. So in this case, that movie was made in 1975. Okay, so this is just converting from Roman numerals to the Hindu Arabic number. All right, now on the next page, here we're going to write each of the following in Roman numerals, Roman symbols. So these are the Hindu Arabic numbers. We want to write them as Roman numerals, like in part A, we got 665. And I want the Roman numeral for that. Well, let's start off by writing 600. Well, 600 will have to be something like 500 plus 100, okay, using these Roman numerals here. So the D represents 500 and C represents 100. And then for the 60, well, I know L is 50 and X is 10, so I can use L, X for that. And 5 is the Roman numeral for, well, 5 has the Roman numeral V. So 665 as a Roman numeral will be DCLXV. Okay. Now part B is the number 43. All right, now for the number 40, that uses that subtractive property that I talked about earlier. Because for 40, which is 50 minus 10, that's going to be XL for the number 40. So XL is 40. 3 uses 3 I's because the Roman numeral for I is going to be 1, so I use 3 of those. So 43 will be XLIII. Okay, part C. 91. Want to write that as a Roman numeral. Well, 90 uses a subtractive property as well, because 90, if you recall, is XC. 90 is XC. And then for the 1, the Roman numeral for 1 will be I. So XCI is the Roman numeral for 91. And then for part D, 2034. 2034. Now, in this case here, the Roman numeral for 1,000 is M. So that means I'm going to use 2 M's for 2,000. And then for 30, let's see. X is the Roman numeral for 10, so I'm going to use 3 X's to represent 30. Now, the 4 uses a subtractive property because it's 1 less than 5. As you can see, it's going to be IV. So for 2034, the Roman numeral for that would be MMXXXIV. Okay. And here's another homework example dealing with Roman numerals here. Let's say I want to write each of the following in Roman numerals, like the number 89. Well, for 89, I know 50 is going to be the Roman numeral. For 50, the Roman numeral is L. X is the Roman numeral for 10, so I can use 3 X's for that. So this represents 80. Now the 9 uses a subtractive property. 9 is 1 less than 10. So I'm going to use IX. So here, LXXIX is the Roman numeral for 89. And then part B would be 5,303. 5,303. Let's try to write 5,000. Okay. Now here we're going to be using what they call bars that I just got through talking about. 5 has a Roman numeral, which is V, but to represent 5,000, I will put a bar above the V, because that's going to represent 5 times 1,000, which will be 5,000. For 300, well, 100 has a Roman numeral, which is C. So I'm going to write down 3 C's. And then 3 I's. Now I only put the bar above the V because I want that to be 5,000. So this right here is your Roman numeral for 5,303. Right, part C, 32. Well, X is a Roman numeral for 10, so I'll use 3 X's. And the Roman numeral for 1 will be I, so I'll use 2 I's. So XXII is the Roman numeral for 32. And then for 302, well, for 300, 100 has a Roman numeral, which is C, and there are 3 of them, so 3 C's. 2 would be 2 I's. So CCCII is the Roman numeral for 302. All right, next we'll look at the Hindu-Arabic numeration system. The Hindu-Arabic numeration system. All numerals are constructed from the 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that's the numeration system that we use today. Place value is based on powers of 10, the number base of the system. And because the Hindu-Arabic system is based on powers of 10, the system is called base 10 or the decimal system. And now we'll look at place value here. What place value does, it assigns a value to a digit depending upon its placement in a numeral, okay? So here we start with the units place or the ones place, then the place value position in front of that would be the tens place or 10 to the 1. The hundreds place would be in front of that, that's 10 to the 2nd. The thousands place would be 10 to the 3rd. Now this goes on and on and on forever, because the next place value position in front of thousands would be 10,000s. The next one in front of that would be 100,000s. The next one in front of that would be millions, and so on. Okay. Now expanded form looks like this. We take each digit and multiply by its corresponding place value position using base 10. So like 6,789, the 6 is in the thousands place, so it'll be 6 times 10 to the 3rd. The 7 is in the hundreds place, so it'll be 7 times 10 to the 2nd. The 8 is in the tens place, so it'll be 8 times 10 to the 1st. And the 9 is in the ones place, so it'll be 9 times 1. So like in this homework example number 5 that I have here, let's say I want to rewrite each of the following as a base 10 numeral. So in this case, in part A, we got 2 times 10 to the 5th plus 8 times 10 to the 4th plus 8. All right, so in this case here in part A, that 10 to the 5th, I can write that as a 1 with 5 zeros because it's in base 10, and the exponent will tell me how many zeros I need. So this will be 2 times 100,000. That's a 1 with 5 zeros. And then plus 8 times, the exponent is 4 for the base of 10. So it'll be 1 with 4 zeros, and then plus 8. So if I multiply 2 times 100,000, that's 200,000. 8 times 10,000 would be 80,000 plus 8. And if I add those together, this will end up being 280,008. Well, just 280,008. And that would be the base 10 number for that expanded notation. Part B, 3 times 10 to the 6 plus 8. Well, that exponent for 6 in the base of 10 that means I can write that as a 1 with 6 zeros. So this will be 3 times 1 with 6 zeros, which is 3 times a million, and then plus 8. Well, 3 times a million would be 3 million. 3 million plus 8 would be 3 million 8. Okay, that's how we write that as a base 10 number. All right, on the next page, for each of the following base 10 numerals, you want to give the place value of the underlined digit. Okay, so in part A, we got 715,839. And notice the 9 is underlined. So we need to identify that place value position. And in this case here, if you think about it or look at it, the 9 is in the ones place or the units place. So the place value position for that would be the units place. 9 is in the units place. Sometimes they call it the ones place for place value. Now, part B, we got 6,721,000. The 6 is underlined. So here, if we go from right to left, this is the units place. This will be the tens, hundreds, thousands, 10,000s, 100,000s, millions. So the number 6 is in the millions place. Okay. All right, in this next example, we want to indicate which digit in 347,256 has the place value shown. So we want to identify the digit that's in the tens place in part A. Well, going from right to left, the 6 is in the ones place, the 5 is in the tens place. So the number 5 is a digit that's in the tens place. Now, part B is the 100,000s place. All right, so again, the 6 is in the ones place, the 5 is in the tens place, the 2 is in the hundreds place. There's thousands, 10,000s, 100,000s. So that 3 is a digit that's in the 100,000s place. Okay. All right, now in this next example, we want to write the following numerals in words. We want to write this in words. Like in part A, we got 48,247,913. And I think I just kind of gave you the answer when I read it correctly. But in words, we read the digit 48, and it's in the millions place, so it'll be 48 million, and then 247 and then we give that 247 the period that it's in. Here it's in the thousands period. So it'll be 247,000. And then 913. Okay, that's how we write that in words. Okay, and keep in mind, we think of periods as this. You have the ones period, and then the thousands period, and then next is the millions period. And also there's the billions period. And each one of those has hundreds, tens, 100 tens and ones, 100 tens, ones, and the same for the billions period as well. And this goes on and on forever as well. Now let's look at part B. Let's say I want to write this big number using words. All right, we got the ones period, and then we got the thousands period, and then the millions period. This 90 is actually in the billions period. So we're going to write that as 90 billion. And then 936, that's going to be in the millions period. So this will be 936 million. And then for the thousands, 878,000. And then 495. And that's it. Okay, so that's how we write this as in words. Okay. Next, we'll look at the definition of a to the power of n. And I think we've seen this somewhere in a previous video before. If a is any number and n is any natural number, then a to the n would be written like this. A is used as a factor n times. That's what this exponent means. Does not mean a times n. A to the n means that a, which is your base, is used as a factor a times. So let's say a to the 5th. This exponent of 5 tells me that 8 will be multiplied, will be used as a factor 8 times. 5 times. So it'd be 8 times 8 times 8 times 8 times 8. And if a is not 0, then a to the 0 will be equal to 1. So any non-zero number raised to a 0 power will be 1. Like 7 to the 0 is going to be 1 by definition. Okay. Now, the way we can use concrete, manipulatives, we can use those to represent base 10. Base 10 blocks are a good example of that, using longs and flats and small unit cubes. Okay. Now, one long would be this right here. That's a row of 10 units here. Here's a unit cube right here. 10 of those unit cubes make up a long. And then for a flat, this is actually going to be 100 units or one row of 10 longs, because 10 of these longs will make up a flat, and 100 of those unit cubes make up a flat as well. And then we have the block. That can represent 1,000 or 10 to the 3rd, because we can use 1,000 of these unit cubes to make up a block, or 10 flats stacked on top makes up a block, or 100 longs make up a block. All right. So in this particular example, dealing with flats, longs, and blocks, what would be the fewest number of pieces you can receive in a fair exchange for 11 flats, 17 longs, and 16 units? Okay, so we have 11 flats, 16 longs, and 17 longs and 16 units. Okay. All right, so now let's start with the units here. I know that 10 units will make up a log. So this is what I would do here. I would subtract 10 units here and trade that in for 1 log. That means I add 1 log here because that's equivalent to 10 units. So if I subtract 10 units from the 16 units, I will have 6 units here. And those 10 units are converted to 1 log, so I'm adding 1 log to that. So this would be 18 longs here. Now bring down the 11 flats. Okay. Now, for the 18 longs here, I know this. It will take actually 10 longs to make up a flat. Okay. So let me bring this paper down here so you'll see that a flat represents one row of 10 longs. So 10 longs make up a flat. So I'm going to subtract 10 from the 18 and convert that by adding 1 flat to the 11 that I have here. So I'll bring down the 6 units. 18 minus 10 will be 8 longs. And 11 plus 1 would be 12 flats. Okay. So I'll have 12 flats, 8 longs, and 6 units here. So using only flats, longs, and units, the fewest number of pieces I will have is, well, actually, I can carry this a little bit further. Because notice here, I got 12 flats. It will take 10 flats to make up a block. 10 flats will make up a block. So let me subtract 10 from the 12 flats, and then I'm going to add to it 1 block. So I'm going to have 1 block here. 12 minus 10 would be 2, so it'll be 2 flats. And then 8 longs, 6 units. Okay. So we'll end up with 1 block, 2 flats, 8 longs, 6 units. Okay, so the fewest number of pieces that we can trade would be 1 plus 2 plus 8 plus 6. I'm adding these numbers together to get 17. So the fewest number of pieces I will have will be 17 pieces that I can use or receive in a fair exchange for 11 flats, 17 longs, and 16 units. Okay. All right, on the next page are other number-based systems. And one of them is the quinary or the base 5 system. Okay, because here in the quinary or base 5 system, we use these numbers 0, 1, 2, 3, and 4. That's it. And then after 4, we use 1 hand and 0 fingers. And then that would represent the base 5, the number 5 in the base 5 system. So it'd be one hand and no fingers. And then next, one hand, one finger, then one hand, two fingers, one hand, three fingers, and so on. Okay, so in the base 5 system is usually this. If we list this by place value. To the right, that's 5 to the 0, which is 1. Then next is 5 to the first, which is 5. And then 5 squared, that's 25. Then 5 cubed, 125. And then 5 to the 4th, that's 625, and so on. All right, now let me show you what I mean by that. Let's say I want to convert 11244 base 5 to base 10. Okay, it's already in base 5. We just want to use this place value chart to convert that to base 10. All right, in this case here, and I want to fill in these numbers using this base 5 chart. So I know the 4 will have to be on the end, then the other 4 in front will be here, then the 2, then 1, and then 1. Now to convert that to base 10, this is what I'll do. I'll take each number in the place value position, multiply it by the number that's on top, like 5 to the 4th, that's of course 625. So that 1 would be multiplied by 625. So it'd be actually 1 times 625. And then this one would be multiplied by 5 to the 3rd, that's 125. So it'd be 1 times 125. And then plus 5 to the 2nd would be 25. So the 2 is in the 5 to the 2nd place. So it'd be 2 times 25. Then that 4 is in the 5's place. It'll be 4 times 5. Plus 5 to the 0, of course, is 1, so it'll be 4 times 1. So 1 times 625 will be 625. 1 times 125 will be 125. 2 times 25 will be 50. 4 times 5 will be 20, and 4 times 1 will be 4. So if you add 625, 125, 50, 20, and 4 together, you'll end up with 824. So 11244 base 5 in base 10 would be 824. Okay, that's how we use that base 5 place value chart to convert from base 5 to our base 10 numeration system. Okay, now this next homework example is somewhat similar to that. You're asked to distribute $1,800 in prize money. The dollar amounts for the prizes are $625, $125, $25, $5, and $1. How should this money be distributed in order to give the fewest number of prizes? Okay, so we got $1,800 to distribute. Now we're going to divide that by 625. Let's start with the largest. So here I want to find out how many times 625 goes into 1,800. And in this case, it'll have to be 2. And then multiply 2 times 625, that would be 1,250. And then if I subtract 1,250 from 1,800, this will be 550. So my remainder is 550. I'm going to use that to come up with the fewest number of prizes I can give for $125. So I'm going to divide 125 into 550. 125 goes into 550, I believe, let's say 4 times. And if I multiply 4 times 125, that would be 500. And if I subtract 500 from 550, I'll end up with 50. So the remaining $50 will have to be distributed with the remaining $25, $5, and $1. Now, let's try 25. Divide that into 50. 25 goes into 50 2 times. Two times 25 would be 50. Subtract 50 from 50, you'll be left with 0. So that means for the $625 prizes, I can give at most 2. For the $125 prizes, I can give at most 4. For the $25 prizes, I can give at most 2. Now for the $5 prizes and the $1 prizes would be none. Okay. So this is kind of similar to the base 5 system here, because if you notice, we got the ones and then 5, 25, 125, and 625. 5 to the 0, 5 to the first, 5 squared, 5 cubed, and 5 to the 4th. Okay, now let's look at the base 2 system. This is also a commonly used system, which is base 2, because it's usually using computers. And it only involves 2 digits, 0 and 1. And sometimes they use a 0 for the off and the 1 for the on, usually on, off. And one of the 2 digits is represented by the presence of an electrical signal and the other by the absence of an electrical signal. Okay. So let's say I had something like this, 10111 base 2. And I want to convert that to base 10. All right, so let's look at the place value for that. To the right, that's 2 to the 0, which is 1. And then in front of that would be 2 to the first, that's 2. Then 2 to the second, which would be 4. 2 to the third, that's 8. 2 to the fourth, which is 16. Okay. That's actually 2 to the third. And if I want to put these digits in their proper place value position, like, let's see, 1 goes here, 1 goes here, 1 goes here, 0, then 1. I want to convert that to base 10. Then that 1 would be multiplied by 16. Not 2, 1. It's either a 1 or a 0. 1 is multiplied by 16. This 0 would be multiplied by 8. The 1 would be multiplied by 4. This one is multiplied by 2. And finally, the 1 would be multiplied by 1. So 1 times 16 is 16. 0 times 8 is 0. 1 times 4 would be 4. 1 times 2 would be 2. 1 times 1 would be 1. Add 16, 0, 4, 2, and 1 together, you'll end up with 23. So in this case here, the number 23 is the base 10 number for 10111 base 2. All right, now let's say I want to convert 27 to base 2. I'm going to convert 27 to base 2. Well, in this case here, if I go back to this place value chart, I use the highest number in the place value chart up here. Now I'm going to extend this a bit. 2 to the 5th is actually 32, but 32 is bigger than 27. I'm not going to be able to divide 32 into 27. So now I have to use 16, which is 2 to the 4th. So if I do 16 into 27, that will go 1 time. 1 times 16 will be 16. 16 from 27 will be 11. Then I take that 11, divide that into the next one, which is 8. 8 goes into 11 1 time. 1 times 8 would be 8. 11 minus 8 would be 3. And then take that 3, divide that by the next place value, which is 4. Well, 4 can't go into 3 evenly. Well, 4 can't go into 3, so I have to put a 0 there. And that remainder will still be 3. So now we take the 3, divide that by 2. Well, 2 goes into 3 1 times. And of course, the remainder of 1 will be divided by 1. 1 goes into 1 1 time with a 0 remainder. So these numbers up here at the top represent what 27 will be in base 2. That's going to be 1 1 0 1 1 base 2. Okay. All right. The last base, the other base, the last one we'll look at is base 12, which is a dual decimal system of 12 digits. Okay. We use a capital letter T to represent a group of 10 and the capital letter E to represent a group of 11. So the base 12 digits would be this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then T and E. T is for the number 10 and E is for the number 11. Okay. All right, so now if we look at this example, here we have E to T, base 12. And I want to convert that to base 10. All right, so now let's think about our place value position for that. It's 12 to the 0, that's 1. The base is 12, so 12 squared. 12 to the first. That's just going to be 12. And then next is 12 to the second. That's 144. And I'll stop right there. And notice that the base remains the same. So if I go to the left, I increase the exponent by 1. And then I fill in the E, the 2, and the T. E goes here, the 2 goes here, the T has to go here. So that tells me for the E, which is actually represented by 11, because E represents the number 11, that would be multiplied by the 144. Plus 2, that's going to be multiplied by 12. And the T, which is actually going to be the number 10, that's going to be multiplied by 1. So 11 times 144 would be 1584. Then 2 times 12 would be 24. And 10 times 1 would be 10. Add 1584 to the 24 and the 10, you'll end up with 1,600 18. So this is what E2T base 12 would be. Now, let's say we want to convert 1277 to base 12. Okay. Now, let me go back up here. If I do 12 to the third, that's 12 times 12 times 12. That's going to be 1728, which is bigger than 1277. Okay. So I will start by dividing 1277 by, in this case, the 144. So if I divide 144 into 1277, that's going to go, I believe, 8 times. And then 8 times 144 would be 1152. 1152 from 1277 would be 125. Then I'm going to take that remainder of 125. That would be divided by, now 144, the next one after that to the right of it, it'll be 12. Well, 12 goes into 125. I know that's going to be 10 times. 10 times 12 would be 120. Subtract 120 from 125, you'll get 5. And then take the 5, divide that by 1, which is the last place value. Well, 1 goes into 5 times. 1 times 5 would be 5. That would be a 0 remainder. So for 1277, we can do the 8, but we can't say 10. The letter that represents a group of 10 would be the T, so it has to be 8, then T, and then 5. And also we write base 12. So it's 8T5 base 12. And then finally, what is the value of G in G36 base 12? And it has to be equal to 1050 base 10. So we're trying to find out what G is. The G, the place value position for the G in base 12 has to be some value of G times, and notice from that place value chart, 144. The 3 in base 12 has to be 3 times 12, and the 6 in base 12 has to be 6 times 1. That must equal to 1050, and we don't necessarily need to write base 10. All right, so if I simplify the left side, this would be 144G plus 3 times 12 is 36, plus 6 times 1, which is 6. That's equal to 1050. Add 36 and 6 together, you'll get 42. So you got 144G plus 42, which will be equal to 1050. And if I subtract 42 on both sides to solve this equation, this will be 144G equaling to 1008. And if I divide both sides by 144, that would mean G has to be equal to 7. So the value of G in G36 base 12 for it to be equal to 1010 will have to be 7. So I'll end up with 736 base 12 to be equal to 1050 in base 10. Okay. All right, so that does conclude this particular video on section 3.1 dealing with numeration systems. feel free to email me or contact me through by phone if you have any questions about the problems that were done in this video and also the homework in my math lab.